Hello, everybody. This is physics. This is going to be a new chapter, and we're going to start talking about nuclear physics today. One of the classes, I don't remember which one, we just started talking about it the day before school was canceled. So, what we're going to do is we're just going to start this chapter over from the get-go, and we'll see what happens. We always have to start off by talking about the parts of the atom because, of course, nuclear chemistry is talking about the atom, the inner workings of the atom, and you can guess by the name, by the nucleus. And so we're going to focus on the nucleus in this chapter. And first of all, let's talk a little bit about the nucleus. How do we know it's there? And it all comes down to Rutherford's experiment of the gold foil experiment. Remember that? We always hear the gold foil experiment. They set up a source of positive particles, and they were going to shoot them through a thin piece of gold. The gold was so thin, they said it was only like 3 atoms thick. And they shot these through, and it hit a detector. Now, the detector would glow when the particles would hit the detector. So phosphorus on it or something, I'm not really sure, but it would glow and they could see spots. This is before computers, really. So they're marking it on a tablet. Every time they see a little dot, they mark it, dot, dot, dot. And they watched this thing for a while, and a pattern started to form. So let's look at our thing that happens here. By the pattern, they realized that the only way the pattern that they got was possible was if most of those particles passed right through and didn't pass right through the material. And some of them were deflected away. And so what they surmised from this was that atoms were made up of small, tiny centers, which they later called nucleuses, right? And they're surrounded by area of negativeness. And that is the gold foil experiment. All right, and that was in 1911. So this is really chemistry. Knowing about the nucleus is pretty new, considering that I had an uncle, a great uncle, that was born in 1901. So it's within a few generations of us right now. Okay, so let's look at this proton, right? And so William Prout is the first person to even decide there's some kind of positive particle. This was in 1815. And he just decided that hydrogens were made of these particles, especially when it was ionized, when the electron was gone. It was a little positive particle. And that's the first they had any concept of these tiny positive particles. And then Eugene Goldstein was studying hydrogen ions again in gases. And he realized that the hydrogen's ion, which, remember, the hydrogen ion is just a proton, right? The electron's gone, was the smallest of the ionized gases. That just means the charged gases. And that was another idea, that there was this little particle there. Now, we go back to Rutherford, because now Rutherford says that those little hydrogen atoms are in the nucleus of all the other elements. And that led to our concept, what we think of right now as protons. Okay, weird story, but all right, now look at this mass. I'm putting this mass down here for a reason. The mass of a proton is 1.67262 times 10 to the negative 27th kilograms. That is very, very small if you haven't figured that out. That is why we use relative mass when we talk about protons. And because protons and neutrons are going to be about the same size, they just give them a relative mass of 1. Now, that 1 is just vague, right? They call it atomic mass units, and it's just saying how many particles or nucleons are in the nucleus is all it really is. And since they're so close in mass, it works, right? So look at the masses here. This is now, I've jumped to a neutron here real quick. 1674993. So that neutron's just a little bit bigger, just a little bit. Okay, and the neutron was discovered by Chadwick in 1932. So the neutron was much later to be discovered. Of course it was. It didn't have a charge. You know, how are they going to discover these small subatomic particles if they don't have a charge, right? And then, of course, the neutron has a charge of 0. All right, now that's our that's our nucleus. Now we call those the nucleons. I have that right here, nucleons, right? And that's generic name for the protons and the neutrons, right? And that's just what we're going to name. Now the electrons, we know the electrons are orbiting around that in the electron shell, or if we get more specific in a different kind of wave orbitals, but we're not going to talk about that because we're not worried about those electrons right now. We're going to focus on the nucleus. All right, let's go up here. All right, and there's the, oh boy, I just said I wasn't going to look at this, but I am, because look at this, the mass of an electron. Way, way small, right? It's even small compared to the protons and the neutrons. They're so small, they don't even count. They don't even count the mass when they're doing the relative mass of an atom. They just count the number of protons and plus the number of neutrons. And that's the mass. That's the relative mass, or also known as the mass number. All right? They don't even count the electrons. They're so small. But even being so small, that electron still has the same charge, equal and opposite to that of the proton. Okay, let's go on. All right, now here's some things we use these in chemistry. If you were in chemistry last year, or you are now, you know these terms already. The atomic number is just the number of protons. The neutron number, you probably haven't heard that term because we usually don't even worry about those neutrons in chemistry. But the neutron number is just the number of protons, or number of neutrons. Sorry about that. Okay, and then the mass number is the number of the protons plus the number of the neutrons. Now, a lot of people start thinking, oh yeah, neutrons and protons have the same mass. They don't, or they have the same number. They can have the same number of neutrons as protons, but it doesn't have to be. All right? Usually in the smaller atoms, their ratio is about 1 to 1. But as the atom gets bigger, there's more and more neutrons. And we're going to talk why that is true, but we're not going to say that quite yet. We're not ready for that. All right, now let's look at our numbers here. Now in the nucleus, we need to worry about those internal numbers now, not worried about charges like we are normally. Now we're going to worry about those. So the mass number is going to go on the top. And on the bottom, we're going to put the atomic number. Now we're not going to say the number of neutrons. You're going to have to use your calculator or your brain to calculate that out, right? So this is chlorine right here. And chlorine has 35 as its mass. The protons are 17. And so we subtract those. And the number of neutrons are what's left. And so if my internal calculator serves me correct, that's 18. So they're not they don't have to be the same number. Okay. The thing that determines what the element is, the ID, all right? What makes it what it is the number of protons. There are elements that have a certain number of protons, and then there's the same exact element that has the same number of protons as that, but then a different number of neutrons, right? They're called isotopes, and I believe that should be our next thing on our slide. Oh, there's a big gap here. Oh, it is. Looky there. So isotopes. Isotopes. Isotopes are elements with the same number of protons. I think I just said this exact thing. With different number of neutrons. Okay, what does that mean? It means it has a different weight, or a different mass, I should say, right? So the mass is different. Mass is not equal. All right, let's look at this here. Here is lithium. Now there's two lithiums. Now look how we have this written, because I'm going to use this. I'm going to use both of these things. And see, this says lithium 6. All right, lithium 6 is talking about lithium that has 3 protons. Now how do I know it has 3 protons? Because that 3 is written right there. And then it has to equal 6. So it has 1, 2, 3. Yeah, that looks pretty good. And it has 3 neutrons. Now, how did I get 3 neutrons? I took 6 minus 3 equals 3. All right, that's one isotope of lithium. And we look over here beside it, and we have lithium 7. So lithium 7 still has 3 protons. How do I know that? Because it's written right here. And now it has to have 1, 2, 3, 4. Yeah, it looks pretty good too. 4 neutrons. And so now its mass is 7 because it has, and let's all count together, 1, 2, 3, 4, 5, 6, 7. 7 particles in its nucleus, lithium 7. Okay, so let's look at another way we have this written. Here, these are some blocks off the periodic table. And this is chlorine. And so in this case, I have 2 isotopes of chlorine. 2. I know there's 3 chlorines there, but I'm just looking at this, and I'm looking at this. Now, 75% of the chlorine that is in our on the earth, right? I can't say about the rest of the universe. That is on the earth is this, right? It has 17 protons and 18 neutrons, right? I just took 35 minus 17. But there is also a chlorine that exists that has a weight of 37. So it would have 37 minus 17, which would be 20 neutrons. All right. So they're the same element. They react the same. Chemically, they react the same. But they do not have the same mass. Their mass differs. Right? This is what's different. Number of neutrons is different. Right? That's what's different. And maybe we can even say the stability, if you wanted to say the stability, but that comes later too. So those things are different. The things that are the same are the number of protons. It's supposed to be a number sign there. Right? The number of protons. Also, all of their characteristics, their chemical properties are the same. Chemical props, right? That would be the valence electrons are the same. The charges they usually form are the same. Everything else about them chemically is the same. If you had those two things together and or had those two things, and you reacted one with one thing and reacted something with the other thing, you wouldn't be able to tell them apart chemically because they are identical. If you found the mass, you'd find the masses were different if you could measure the mass. I hope that makes sense. Now, on the periodic table, because we know that we have these different isotopes of this same element, and we know that they're mixed together all the time. They're not separate, they're together. If we have chlorine, 75% of it is the chlorine 35, and 25% is the chlorine 37. But if we take the average mass of those two things, it ends up being 35.5. And so on the periodic table, we use 35.5 as the mass because in nature, that's how we find it. Because we don't want to have to worry about these different isotopes at any other time. I hope that makes sense. All right, we're going to move to the next section. There are four forces in nature. I know this doesn't sound like it's right, but it is. There are only four forces in nature. And those four forces are gravity, electromagnetic. And now electromagnetic, you're going to see me write EMF, electromagnetic force, because that's the easy way to do it, right? And there is the strong force, and then there's the weak force. All right, so we have those four forces. Now, we've talked about the first two, right? Gravity and electromagnetic forces. We talked about gravity when we talked about, Newton's universal law of gravitation and that kind of thing. And we know how gravity works. We know what gravity is. We know it's between the masses. So it's a force. No, they really don't understand it much more than that, but it's between masses. It's between two different masses. Right? And it is the longest range. Right? It goes out all over the whole entire universe. Long range. And it goes through the whole universe. And it is also, and this is going to seem weird because we have one named the weak force, but it is the weakest of the forces. I know what you're thinking. It holds us to the earth. It has to be strong. It's holding the planets in place. It has to be strong. It's not strong compared to these other forces, right? It's just abundant. When there's large masses, we can feel the effects of it, but we can feel the effects of the other things too. All right, our next one. Electromagnetic forces are forces between the opposites, the opposite charges, the opposite sides of a magnet. Electromagnetic force, right? So it's the force that's between those opposites. All right, and it has a medium range, right? And we've used the Van de Graaff generator when we put our hand on top of it, right? It made our hair stand up, and we could feel the force around it, and it made the little pieces of paper move, and it made the little aluminum foil jump around the room. It has a range, but it's not like gravity. It's not going to reach all the way to the stars. It's going to be in a smaller area, and we're going to call that a medium range. And it's pretty strong, though. It's a lot stronger than gravity, that's for sure, right? Because it can like a magnet can pick up a lot more. A magnet can pick a car up, right? And so it has a really strong, it's pretty strong. I'm going to say that it's medium strong force, right? So it's in the middle there. Now, remember how these work between opposites. Oh, I'm going to change this. I said between opposites. I'm going to put in likes. And I should have said this, but I skipped it. And we're going to say this right now because we can do that. Opposites attract and likes repel. And we know that, but I'm just going to say it. All right. And we know how that works, right? Two positives are going to repel each other apart. Two negatives repel each other apart. Positive, negative attract together. And we did Coulomb's law for that one. Remember that? Right. All right, strong force. Now, strong force is going to be the force that holds or binds the nucleons together. So it bonds these, so it holds the protons, the neutrons, the proton, neutron, the neutron, holds those things together. It holds the nucleus together. It's between the neutrons and neutron, proton and proton, and of course neutron and proton. All right, so it's between those things, right? It holds them together. That's why they stay together. It is the short range, very short range, right? The atom's nucleus is so small, right? This is even smaller than that. It has to be touching almost. So well, actually, I shouldn't say almost. It has to be touching. So it's that thing that's just going to take that proton and make it stick to another proton, and it's right there. If I can break that apart so it's not touching, they're not going to be held together by the strong force anymore. Right? And the strong force is the strongest force. Okay, finally, the weak force. Now, the weak force is confusing, right? And it's another nucleus force. It's a force in there. Different things I read about it, it's very vague. The one book said it also works in nucleus. That's what it said. That was the whole definition of it. So I used to think of it as the force between the quarks. And the quarks are those little teeny particles that make up the protons, the neutrons, and the electrons. Now, is that 100% correct? Probably technically not, but we're going to go with it. It's short. Its range is also short, right? And it's not as strong as the strong force. Right? It's okay. All right. Now, let's look at these forces in the nucleus. Of course, the weak force is in the nucleus also, right? And the strong force, and the electromagnetic force, and all of them are in the nucleus. Let's draw some nucleus here. So, say we have some particles, and I'm just going to draw a helium because that's short and easy to do. Okay, let's put some charges in here. Let's call the green ends. Let's call these positives. Okay, now, we know gravity is holding between these particles, but the mass is so small. Right? So there's a small force of gravity in there, but not enough to make much difference, right? The weak force isn't really holding those particles together. It's holding the particles themselves together, right? So it's holding that, making that proton a proton, making that neutron a neutron. It's not necessarily holding those things and keeping them together. It's keeping the neutron a neutron and the proton a proton. So we're not going to worry about that right now. But what we're going to worry about is this strong force that's holding them together. And then we also have two positive particles. And the electromagnetic forces between those positive particles are pulling, actually more like pushing it apart, right? And what's overcoming that is this strong force that holds them together. So the role, what happened there? So the role of neutrons, right? What do neutrons do? Why do we even have them if they don't do anything? They don't have a charge. They have a weight, but they vary. What they do is they are spacers. Just like when we talked about the Van de Graaff generator, right? When you were further away from the Van de Graaff generator, right? That's supposed to be a hand. Maybe a spark shot to you, but if you went further away, it didn't. Electromagnetic force is affected by distance. So if you can take more neutrons and you can put them in between those positive particles and you can spread the size of this thing out, right? And you can make the atom bigger, you can make this space bigger, then those repelling forces won't be as great. Small atoms. Small atoms, it's not that important, right? Hydrogen only has one. It only has one proton. Right? And no neutrons. Why? Well, there is an isotope that does have some, but and no neutron, because it doesn't need them. It doesn't need them because there's only one positive particle. It's not trying to separate anything. But as the atoms get bigger, they're usually a 1-to-1 ratio. Right? And as you get bigger and bigger and bigger, you need more neutrons to spread out the electromagnetic force. That's why we have neutrons. Okay. I'm going to do this last little section. I'm going to call that a day on this. We're going to talk about quarks. Okay. There are 6 different types of quarks. There's different things on this. It gets weird and wacky. And I don't want to do weird and wacky, right? I'm just going to do normal here. So we're going to say there's 6 flavors of quarks, 6 types. They use the word flavor for that. I don't know why, but it sounds cool. And there's up, there's down, there's strange, there's charm, there's bottom, and there's top. So those are our 6 quarks. Now, we're not going to worry about that. Those little particles are what make up all the other particles that we have, right? And we're not really going to worry about what all that means right now, but we're going to worry about our 2 things that we do want to worry about. Our proton and our neutron. Is that too dark? Okay, so we have a proton and our neutron. Now, the quarks have little charges, and the ups charge is positive 2/3. The down quark is minus 1/3. All right, it says it right there. That's the charge of the quark, and that's comparison of an electron. Okay, so why is a proton positive? 2/3 plus 2/3, that's 4/3, minus 1/3 equals positive 1. So a proton has 2 ups and 1 down. A neutron has 1 up and 2 downs. And so if you look at it, it's 2/3 minus 1/3 minus 1/3, which equals 0, and it has a charge of 0. So neutrons have 0 charge, and the protons have +1. All right, there's all sorts of different combinations of quarks and different particles, and again, we're not going to talk about all that stuff. Okay, so I have that written out here. I just re-explained it, and I'm going to call that a day. Now, let's look at this paper. So what I want you to do on these papers is, follow along with the notes like we're doing, and we're filling stuff in, and I highlight stuff and I draw pictures and stuff like that. I'm just trying to help you understand this. And then we're going to get down here at the very bottom of the paper, and I made up some questions. And I have them marked. Whoops, I just passed them. So, parts of the atom, right? So these are questions. We have 12 questions for this first thing. And what I want you to do is I want you to answer these 12 questions. Now, some of these are, a little bit longer answers. You're not going to be able to squeeze your answer in this little space right here, right? Write it on a sheet of paper or type it up. I shared the Google Doc with you so you can push return and you can type up your little section there. If you do that on the Google Doc, if you'll change the color of your font for these questions, it'll be so much easier for him to find out what you wrote, and it'll be so much easier for me to grade. Okay, so we have different questions about masses, why they're the same or why they're different, what isotopes are, and then we get into some of the nomenclature, or the way we're going to write, not nomenclature, but the way we write it, right? So we're going to find out what these X's are. So we know what the mass is, we know what the atomic number is, and you have to get your periodic table out and see if you can figure out what those are. Okay. Then it asks for what the number of protons, neutrons, and the weight is of those isotopes from problem 6. So you're going to go back in there and you're going to find out. You don't need to look anything up. Even if you miss the ones from 6, you'll still get those right. The weight's the top number, the protons are the bottom, subtract to get your neutrons. And this is going to ask different questions we talked about, but if you answer those 12 questions, we're going to call that day 1, and that'll be lesson 1. Tomorrow we'll go over the discovery of radiation. I'll put it up tomorrow or the next day, probably tomorrow since it's a short week. And then you'll have to answer those next questions, right? And then our last section is radioactive dating, and I'll put the notes about that. And then you'll have to answer those questions. So I'm trying to get 1 hour a week of homework. And so right now I'm not sure if it's going to be 2 sections this week or 3 sections. We'll see how long this video is when I turn it off in a second, and I'll add up the questions. I think we're just going to do the first 2 sections for this week. Next week we'll do the 3rd section, and then we'll have a new lesson coming after that. All right, I hope that answers all your questions. If you need any help, you can always use Google on these things. I hit the Google hard on this, and I also used a few different physics books to get these lessons and things. So if you look over the notes and you followed along and you wrote down the little things I told you, it should answer most of your questions. All right, well, have a great evening. It's evening here now, so have a great morning or evening, whatever time it is for you. And if you need any help, just send a reminder out to me. And ask a question on that. And when you do your questions and you turn them in, please send them through email or Gmail, because I want to collect both the outline and the questions. And so if you do it through Gmail, then you can just, if you're doing it right on the paper, you can just share that back with me. If you're typing it, if you want to print it out and write your stuff in like some people do, that's fine. You can take pictures of that and send it to me. The Remind app has its limitations, and one is sending more than 1 paper at a time. So, all right, well, thanks a lot, and stay safe out there.